Hello everyone. Today I'm going to talk about stochastic ordering in a very brief sense. Basically, stochastic ordering is related to dominance among random variables. Let's start with the definition. A random variable x is stochastically larger than a random variable y if for any given c, the probability of x being larger than c is greater than or equal to the probability of y being larger than c. If we multiply both sides by -1 and add 1 to each side, then we can have an equivalent inequality for the same definition. And more generally, if x and y have cumulative distribution functions f and g, then x is stochastically greater than y if the value of inverse CDF of x, which is f bar in our case, is larger than the value of inverse CDF of y, which is g bar, for any given c. Similar to the first case, we can manipulate the inverse CDF inequality to obtain an inequality in terms of cumulative distribution functions. Let's continue with that example. Let x be uniformly distributed between 1 and 3, and let y be uniformly distributed between 1 and 2. By letting f and g be the cumulative distribution functions of x and y, we can simply calculate the CDFs and inverse CDFs of given random variables. And after this calculation, if we compare f bar and g bar, we can see that f bar c minus g bar c is always greater than or equal to 0 for any given c. And as a matter of this fact, we can simply say that random variable x is stochastically larger than random variable y. And the same thing can be seen in this graph. The upper graph is the graph of cumulative distribution functions, whereas the lower one is the graph of inverse CDFs. And as seen in the lower one, the inverse CDF of random variable x, which is f bar, the blue one, is always greater than or equal to the inverse CDF of y, which is the red one, g bar. In the last part of the discussion, I'm going to discuss the relationship between expectation and stochastic order. If x is stochastically greater than y, the expectation of x is greater than or equal to expectation of y. The proof is very straightforward for the case where x and y are non-negative random variables, because in this case we know that the expectation can be written as an integration of inverse cumulative distribution functions from 0 to infinity. And in the expression, we know that the value of left-hand side integral is greater than or equal to value of right-hand side integral. The reason for that is probability of x greater than c is always greater than or equal to probability of y greater than c due to the stochastic dominance of x. For the general case, the proof is a little bit more difficult. We can represent a general random variable as a difference of two non-negative random variables. And as seen in the expressions here, x can be written as x plus minus x minus, and y can be written as y plus minus y minus, and x and y are x plus, x minus, y plus, y, and y minus are all positive random variables. Basically, the plus random variable represents the positive component, and the minus random variable represents the negative component of the random variables. We can write, after defining these, we can write expectation of x plus as the integration of probability x plus greater than c from 0 to infinity. Since this integration is from 0 to infinity, we can simply replace probability x plus greater than c by probability of x greater than c. And since we know that random variable x is stochastically larger than random variable y, similar to the first case, we can simply say that the first integration is greater than or equal to the second integration. And finally, probability of y being greater than c can be replaced by probability of y plus being greater than c, since the integration is again from 0 to infinity. And the last integration in this expression is equivalent to expectation of y plus. Therefore, the expression shows that expectation of x plus is greater than or equal to expectation of y plus. And in a similar way, the second expression shows that the expectation of x minus is less than or equal to expectation of y minus. Then combining these two results, we can simply show that expectation of x is greater than or equal to expectation of y, and this completes the proof. This is the end of my discussion, and thank you for listening.